Hello. In this lesson, we're going to look at the models of the atom that lead up to the current model of the atom, the quantum theory model. In addition, we're going to look at the properties of the quantum model. Just the overall properties. We'll get into electron configuration next time. First, we're going to look at the nuclear model, which was theorized by Ernest Rutherford. He came up with his theory based off of his experiment that we refer to as the gold foil experiment. During the gold foil experiment, what he did was he fired alpha radiation, alpha particles, which are simply 2 protons and 2 neutrons, although he didn't know that at the time. It's just positively charged radiation. He fired this at a sheet of gold, pure gold, that was flattened into as thin as he could make it. And what he did was he had a detection system set up around the gold to measure where the particles deflected to. The hypothesis was, if the plum pudding model from Dr. Thomson was correct, then all of the particles should contact with the back portion of the sensor array. But this wasn't what he saw. Instead, what he saw was the alpha radiation was deflected all around the sensor array, like it was bouncing off of something. What he did was, first, he discovered the positive particle. Because if they were being deflected by something, he knew that it had to be the same charge as the radiation he was shooting at it. So he discovered what we refer to as the proton, the positively charged particle. Second, he discovered that in the center of the nucleus, or I should say, in the center of the atom, there was an extremely, extremely massive and dense thing. And this is what we refer to as the nucleus. We know that the nucleus contains those mass-containing particles, protons, and also neutrons. The third thing he discovered, because a good amount of the radiation did pass through the atom, only a handful of the things that were deflected, only a handful of pieces of radiation, for lack of a better term, were deflected. The rest passed through. So he explained that while there is this extremely dense nucleus, the rest of the atom has to be mostly empty space. To give you for instance, if you imagine a football field as being our atom, and not even just the football field, the entire stadium, an entire professional football stadium is the size of an atom. The nucleus would be the head of a pin in the center of the field. So this nucleus had to be extremely, extremely massive, meaning that there was, not that it was huge, but there was just a lot of mass there, meaning that it was really, really dense. So, as with any of these models, there were problems that needed to be explained. And this model in particular could not explain the way that electrons moved or acted within the atom. And one of Rutherford's students, Niels Bohr, came up with the next iteration of the model, which is what we refer to as the planetary model. As I said, this was theorized by Niels Bohr. The model gets its name from the orientation of the electrons. They are in distinct orbits around the central nucleus, the way the planets orbit the sun. He came to this conclusion, and he came up with the idea based on an experiment he did. Now, the experiment he did was much more complicated than the one that we looked at. But in essence, it was very similar to the flame test introduction that we did. So he came up with this idea for what we call energy levels, or orbits. His explanation was that the electrons have to orbit the nucleus, and they are in these very distinct energy levels. Electrons, he said, could jump between level to level depending on whether energy was either added, meaning that the electron would go up to the next level, or whether energy was released, in which case it would go down to a previous level. He talked about something that we refer to as the ground state. The ground state is the lowest possible energy state for an atom. What this means is the electrons are in the lowest possible energy level that there is. So, if we think of this like a ladder, then the ground state would be the furthest rung down on the ladder that an electron could be in. When that bottom rung is full, then they go to the next level. And then when that is full, they go to the next level. And so on and so on and so on. So, the ground state being the lowest possible state, what Bohr saw was when energy was added, something happened. After a moment, there would be a release of some color of light. So what he theorized was that there had to be an excited state as well. An atom will absorb energy, which causes electrons to jump to a higher energy level. So when energy goes in, the electrons get more excited, causing them to go to the next rung or two rungs up. But the atom doesn't want to stay in this state for long. Eventually, it's going to start releasing the energy, which we saw in the form of color for the flame. When that energy is released, the electrons drop back down to the ground state, the lowest energy level that they can be. And like I said, this acts like rungs on a ladder. Electrons need to be on one level or the next. Just like on a ladder, I can't rest my foot in between two rungs. Eventually, I have to set it down on one or the other. Just like with this, electrons can't exist in between energy levels. They're either on one level or the next. So, a term that we're going to be using, and Bohr called this a quantum. For an electron to move from one energy level to the next, there's a distinct amount of energy that needs to go into the atom. Once that amount of energy goes in, the electron will jump 1 or 2 or 3 or however many energy levels it does. And same thing going in the opposite direction. To drop down to the lower energy levels, it needs to release the same amount of energy. Now, as with the Rutherford model, there was still some problems. Obviously we don't use the Bohr model now other than for academic purposes. The main problem was that this model only worked with atoms that had one electron. So a hydrogen atom or a positive helium ion, that lost one electron, or a lithium ion that lost 2 electrons, and so on and so on. It only worked for atoms that had 1 electron, because it did not take the interactions from other electrons into consideration. As we know, negative charges will want to repel each other, just like positive charges want to. That's why there's a strong nuclear force to hold the nucleus together. Second, is it very much oversimplified electron movement. By describing the electrons as planets that orbit this central nucleus, he was giving too much of a discrete explanation. With things that are that small, something that is smaller than an atom, movement gets to be very weird and unknown. Which brings us to the next model. The Schrödinger model, also known as the quantum model. This is our current model of the atom. One of the main ideas is that we cannot give a discrete location nor describe the exact movements of an electron. It's simply too unknown to us. We kept the energy level idea from Bohr's model because we do know that there are these energy levels still there. These are still quantized. But as opposed to having this singular electron that orbits the nucleus, what we see is that the electrons behave more like a cloud. What this means is that electrons can, in all reality, appear anywhere in that given cloud. They have an equal probability of appearing or existing anywhere in that given level at any time. So if we're looking at that first energy level and we know there's 2 electrons in there, we don't know exactly where those 2 are. We just know they're somewhere in that level. And the example that I like to use to talk about this is, think of the blades on a spinning fan. That blurring effect that we get from the spinning of the fan, that is kind of how the electrons act. We know that the blades of the fan are in there somewhere. But if a fan is spinning that fast, we don't know exactly where they are. Just that they're somewhere in that blurred area. We know they're somewhere in that given area at some time. So to describe this, we use something that are called quantum numbers. These are various ways that we use to describe a particular electron's behavior or its likely location. And I mentioned this in class. We talk about 4 sets of them. We'll only be dealing with a few of them regularly, but it is important for you guys to know them all. Starting with n. N is what we refer to as the principal quantum number. This corresponds with the energy level that we are discussing. And this can only be from 1 to 7. In theory, we could have energy levels that are higher than 7, but we don't have any atoms that are big enough to where they would have that 8th or 9th energy level. So these only really exist from 1 to 7. And in these energy levels, we have various shapes, which we will talk about next. But as we move further and further out from the nucleus, we see an increase in energy levels and an increase in size. The next part of the quantum number is what we call sublevels or subshells. I will try to use sublevels more frequently, but both of these terms apply and they're talking about the same thing. A sublevel is within a given energy level. There are various sublevels with slight variations in energy, and they have different shapes. And there are 4 that we will deal with. They can all hold a different number of electrons. So depending on the sublevel, there can be more or less. The first one, and the smallest sublevel, well, smallest, is the S sublevel, which we refer to as sphere. Because of the shape. It looks like a shape. or not looks like a shape, it looks like a sphere. It can hold 2 electrons, and it is found in all energy levels. So from 1 to 7, there is a S sublevel. Next is P. The P sublevel we refer to as peanut because of its shape. It is kind of this dumbbell shaped like a peanut. It can hold 6 electrons. And this is found starting in energy level 2, N equals 2, and it begins with the element boron. The next is D, or double peanut. Once again, because of the shape, it looks like 2 of the peanut shells crossed. In this orbital, there can be up to 10 electrons. And this is found starting in energy level 3 and starting with the element scandium. Lastly is sublevel F, or flower. There can be up to 14 electrons found in here, and this is from from energy level 4 and up. And it begins with the element lanthanum. Those are our 4 sublevels and their shapes. We'll go a little bit more into this and how they can hold the different electrons in just a moment. The last 2 parts of the quantum number are atomic orbitals and spin. Atomic orbitals, simply put, are the probable locations for finding electrons. So if we look at the shapes from the previous one, none of these are 2-dimensional shapes. And because they're not 2 dimensions, they all have various ways of orienting themselves. For instance, if you take the peanut, the P orientations, we see that they can arrange themselves horizontally along the x-axis, horizontally along the y-axis, or vertically. Each of those is what we refer to as an orbital. Each orbital can only hold 2 electrons. So, S suborbitals only have 1 orbital. P has 3. D has 5. And F has 7. So because they have these different orientations, they can hold twice as many electrons as they have orientations. 2 for each orientation. The second part of the second quantum number that I want to talk about on this slide is what we call spin. This is, simply put, it's a quantum mechanical description of how electrons move. And the best description I can give this, because obviously, like I said, the movement of electrons is so much more complex than I'm boiling it down to. This is like very high level quantum physics type of thing. To just give you an idea, spin is simply if you have an electron that's, let's say, moving clockwise. The other electron that it would be paired with would be moving counterclockwise. One is moving in one direction, the other is moving in the opposite direction. And that about does it for quantum numbers and the quantum theory in terms of the main properties. Last thing I want you to do is here is the summary for what I've just described. In particular, the principal energy level, how many sublevels are present, the type, and the maximum number of electrons. Okay? So, until next time.